Hello, everyone. Welcome. Thank you for joining us. We'll get started shortly. We'll just let folks join for the next minute or so, and then we'll dive right in. All right, and we have a lot to cover today, so let's get started. Thanks again, everyone, for joining us for today's Geospatial Analytics and AI at Scale workshop. We are so thrilled to have you. We couldn't be happier to show you this presentation and walk you through everything. So let's kick off. So for today's event, you will receive a copy of the slide deck, recording, and notebooks that are presented today. So keep an eye out on your email tomorrow. We will be sending those out so you can access it later on. Please leverage the Q&A function to ask any of your questions at any time. We have our team of experts on the line here to answer those questions as they come in, and we highly encourage you to engage with us virtually. This is what makes it really fun for us. We get to hear from you and kind of make sure that you are able to follow along throughout the event as well. And then please participate in our poll. I'm going to launch that right now. It's just a couple questions. Would love to get an idea of who's here in the audience with us. So if you don't mind just taking a few minutes to do that would be great. So for today's event, you will hear from our amazing presenters. You're going to hear from Rob, who's our account executive here at Databricks, Mark, who is the engineering, insight, and analytics technical lead at Stantec. He's our customer. We're so excited to hear your story, Mark. Chris is going to be presenting as well from Databricks. Milos, you're going to hear from him on the more technical portion as well, following Chris. And then we'll be ending with Kent and then ending in some questions today. So I'm really excited for you to hear from all of our team members. Sorry, I already launched that poll, so we'll keep that running for a few minutes. And then with that, I will introduce or go over the agenda, excuse me. We're going to do a Lakehouse overview for today. We're going to cover the geospatial on Databricks and challenges, geospatial processing flow and H3 indexing, mosaics, point polygon challenges, joint strategies, BNG index system, and Spark tuning. So a lot to cover. So let's dive into it. Rob, would you like to take over from here?
Yeah, sounds good. Share here. Perfect. So thanks again, everyone, for joining. I'm going to take a couple minutes for those who are new to Databricks just to talk about who we are as a company, a little bit about our observations in the market, really which drives, how we develop, how we help organizations thrive in the data and AI space. Then I'll hand it over to Chris to talk about, what we do and what we bring to market. So first, a little bit about Databricks. Starting just before Databricks was officially an organization, there were 6 folks out of Berkeley Amp Lab, and they were pursuing a better solution to help address the evolving space of big data, the limitations of Hadoop, the limitations of MapReduce, and fast forward and came the introduction of Spark as an open source project. And they were evangelizing the adoption of Spark and quickly realized that without an enterprise wrapper to make it easier to manage, give it performance optimizations, basically make it ready for enterprises to adopt as a standard, they're going to have a hard time really enabling the impact that Spark can have. So that in 2003 came the inception of Databricks, and the world in the data and AI space has continued to evolve. So we didn't rest laurels around Spark, although that's how many organizations or many people still associate Databricks. But through time since 2013, we've also introduced several open source projects that have had really strong adoption. Delta Lake to help organizations better access and get performance and reliability out of their data lake. ML Flow to simplify the entire machine learning lifecycle, and et cetera. So we continue to evolve at a very rapid pace to address and get in front of the changing landscape of data and AI. So really what we try to achieve is taking the capabilities that have really given, the FANGs, Facebook, Amazon, Apple, Netflix, Google, Microsoft, their reputation of being very data and AI centric in how they operate, but not everybody has huge development teams that they can go and do this in-house. And everyone is becoming a data and AI company now. It doesn't matter if you're a 100-year-old organization that is a leader in your space and trying to go through an evolution and a transformation, or if you're a digital native disruptor that's moving super fast, trying to shake up the industry that you support. Everyone is leaning on data as a core component to their company. A lot of this actually involves geospatial. The really cool thing, we work with organizations across all different sectors, and represented here in the attendees today, we see, it's not just GIS supports one specific type of organization. There's a common layer of GIS in many of the use cases across all of these industries. So when we look at the market around data and AI, there's kind of four truths that we see. The first is that organizations are fully embracing machine learning and AI as the future. Everything they're talking about is ways to adopt it, ways to make the data available to the organization, and making this a lifeblood of the organization. So how to get better, faster, more confident insights through data, how to reduce risk to their organization across several facets, and how to do this while controlling costs. ultimately, data and AI should be used to either make or save organizations money, and having a cost-conscious control of this is critical. And when we talk about data and AI, we use this slide a lot as almost a level set. A lot of organizations or people think about data and AI, as this little box that we see in the middle around the ML code. But the reality is everything that goes into making data accessible to the organization, being successful in productionizing machine learning requires many components. And that's really what we'll talk about today through the course of the session. So another truth is that there's a prevalence and open source is really emerging as a leader in terms of adoption and strategically what organizations are leaning on to achieve success in data and AI. So the reasons why is the breadth of the ecosystem. So when you look at all the different components, integrations, APIs, it's going to be a huge theme to the session today, obviously, in the geospatial space, really lends well to that. The cost of portability, how can you migrate your solution? This is a very fast moving space. So being able to be portable, have that latitude and transferability is really critical. And then the learning curve around open source, much easier to acquire and retain talent compared to proprietary IP and very specific skill sets. The next truth is multi-cloud. So organizations, even if they've started with one cloud, they're starting to develop strategies, and we see this in many regions now, is a full-on multi-cloud strategy. So having a solution that could work with the service of choice given any cloud vendor. And then a simple data architecture. So eliminating the complexity. Ultimately, how to provide these capabilities, how to future-proof yourself while still maintaining governance and security requirements, the right data lineage, avoiding multiple copies of the same data, the silos that naturally happen in many of the legacy architectures, how to simplify the ability to take advantage of the data and AI potential in your organization is really critical. And this is where a lot of organizations are currently struggling. So I'm going to hand it over to Chris Chalcraft to talk a little bit more about the struggles and then how we solve for this. Over to you, Chris.
Yeah, thank you, Rob. Let me just get the share here. Can you see my screen okay?
We can, yes. We just present mode would be good.
Yeah, thank you. Yeah, so one thing that we really see with our clients is that everybody's trying to build some of their data and AI capabilities within the organization. They're trying to become a data native company, but really they're getting bogged down with this siloed stack, right? That has their data sources coming in from a variety of different areas. And there's all this disconnected system of tools that, you know, some people might not know across these different disciplines, right? So a data engineer might have a completely different stack than, you know, the data science and ML team, right? And it really creates these barriers between the individuals in the company. And so, you know, instead of trying to deal with all of this complexity around, you know, how to actually process the data and then, you know, transition it to the next individual down the line, you know, we really want to make sure that we can streamline this process and make sure that, you know, we create this, you know, unified approach where you break down those barriers. So this is where the Lakehouse comes in, right? And, you know, so for some of you who are not familiar with the term, you know, we're talking about really a combination of the best features of a data lake and a data warehouse together. So, you know, because there is this like hodgepodge of tools, right? That you'll have like, it's pretty expensive and resource intensive to manage. What the Lakehouse will provide is you'll get the benefits of the data lake where, you know, you'll have handles all your different data types, your open format, and being able to cater to the big data ecosystem, right? But, you know, the data lake itself, you know, is sometimes, you know, in recent, historically, it's been pretty poor at BI and, you know, prone to a lot of like complex data management issues. Right. And so, you know, the data warehouse, on the other hand, you know, while it's been really good at BI, you know, may not be able to support some of your workloads like, you know, the ML workloads or the streaming workloads, right? And so the Lakehouse really tries to bring them together. And under the thing that really brings the performance and reliability to the data lake is the Delta format. And so, you know, the Delta format, you know, it's, you know, while it's not a focus of this talk, you know, we really want to focus heavily on geospatial. This is, you know, pretty key to making sure that Lakehouse vision can be a success, right? And so when you look at your data lake now, you can go and you can trust your data. You can have all the data governance and different access control, as well as the structure and the performance aspects of it. You know, and when you think of a geospatial workflow, you know, you're ingesting it from a lot of different file formats, you know, and you might want to have that Delta lake as a place to store. And I think, you know, you'll see from our customer story later, Mark, he was able to use Delta in his geospatial processing flow. So yeah, so the Lakehouse offers you know, a great path, and really we're trying to cater to making sure that you have the data engineering, the BI and SQL, and the data science and ML built on this platform of, you know, security, governance, and, you know, a unified data foundation. So when we look at, you know, some of the core things that Rob mentioned, right? Simple, open, and collaborative. So simple is, I'd say, you know, one of the strongest motivators for this, right? Really trying to reduce the complex architecture that gets set up, right? And all the overhead and management that's required to have that, right? And giving people this, you know, common platform for all these data use cases, right? And that works across clouds, Azure, AWS, and Google Cloud. The next one, Rob also mentioned, you know, is open. So the core open source technology that really underpins, you know, the Databricks platform, Spark, Delta, MLflow, right? A lot of the founders and many people at the company are contributors to these open source projects. And, you know, Databricks makes it easy for us to use these, and then doesn't provide a lot of lock-in when using these formats. And another benefit of being open is that, you get this, this great data ecosystem of all these tools that people can either develop or have different, partner integrations to work with Databricks. So you could be assured that, regardless of your workflow, there will most likely be some development that will help position you for, future business use cases and keep up with the advancing technology. And then finally, and I think this is one that gets overlooked quite often, is just like bringing people together in this collaborative workspace, not having to deal with the handoff and, the telephone type things that might happen with your data along that process, right? And it really gives people a more consistent view and allows you to iterate more rapidly in your projects. Okay, so that was a quick overview of the Lakehouse, and so now I want to hand it over to Mark. I've had the pleasure of had a few engagements with Mark with the Stantec team, and in all honesty, they're just really curious about Databricks and the technology it had to offer, but really I didn't do much guidance. They really just took the key pieces that really worked for them and were able to go into their specific geospatial use case. So I'll let Mark tell you about that. So Mark, I'll hand it over to you.
Thanks, Chris. Share my screen here. Okay. All right, can everyone see my screen?
Yep.
Yep.
Okay, great. So thanks, Chris, for the introduction. And yeah, as Chris mentioned, we were able to integrate the Delta Lake and Databricks into our geospatial workflow. And in our case, we're using the geospatial analytics to build a machine learning model to predict flooding rapidly at a speed that currently can't be achieved using traditional physically based models, which has benefits for allowing one to predict flooding from a forecast, for example, and give warnings to people when a flood event is about to occur. So the agenda, I'm going to quickly talk about Stantec and the platform that we're working on for machine learning. I'm going to discuss the problem of flood hazards, followed by how we're approaching the problem by merging data science with engineering expertise in the civil engineering field, and then how we're using the Delta Lake for the storage and use of our geospatial data, and finally how that blends into the use of Databricks for building our machine learning model and process. And then finally, I'm going to discuss some of the results from our flood machine learning model that we recently have deployed as an API for use. So Stantec's a company of around 20,000 plus individuals. It spans the globe, all 6 continents except Antarctica. And we are working on a platform which you can look up on stantec.io. And the reason is we believe that digital science, engineering, and design can be easier, faster, and equally as effective without compromising safety and security. And I would add to that, we also believe that we can find answers that we traditionally couldn't find with engineering approaches of the past up to the present. So we can find patterns in data that can help inform engineering decisions in everyday life and help make the public safer, for example, for flooding. And so we exist to enable a new wave of digital science and engineering that will deliver on our vision to double the capacity of scientists and engineers, as well as, I would say, finding new answers that we otherwise couldn't find. And we plan to do this by enabling architects, scientists, and engineers to apply knowledge and expertise through innovative digital solutions, including machine learning and use of Databricks and other resources that have now become available. So why is flooding important? Well, on average, in the United States alone, I'd say around 50 to 100 people every year die from flooding. And much of that is caused by flash flooding. So if you followed the recent storms that went up the East Coast, the hurricanes in the late summer, there was a pretty catastrophic flooding in New Jersey, and quite a few people perished. And a lot of that was from flash flooding. So flash flooding, I'll explain what that is, but it causes 80 to 90% of the annual flood deaths per year. And many of these are from folks in their cars or crossing the street. So people that don't have warnings as to where the flooding is occurring, so they're driving their cars into these situations that are quite hazardous and that need to be avoided. So if we can create a process that can warn people, that can provide a physically based model result, but much faster, and it provides the ability to provide that information from a weather forecast. Instead of just getting, I'm sure everyone's received a warning on your phone from the weather service, there's a flood warning in the area, but you never know where exactly the flood's going to occur. So it's hard to take action on that, because you could be in your house, there's a flood warning, but do you know that the flood's going to affect you? And that's why I would say in New Jersey, a lot of people died in their basements because they didn't know the flood was going to affect them. So flash flooding, it occurs when you have an intense rainfall event that overwhelms the drainage system of an area. So it could be an urban drainage system as well as a natural drainage system. And what accompanies the overwhelming of the drainage system is also these concentrated flows of water that wash cars away, that can wash pedestrians away. And this is the type of flooding that we're focusing on predicting. And the way we do this is we merge the data science process with the engineering expertise of within the company. So we have a company of 20,000 engineers doing this work on a daily basis. And the challenge is, how can we take that expertise and merge it into a machine learning process that can provide results that would be acceptable to the engineer at the end of the day? And so we start with the raw data, which is a digital elevation model, land use, other attributes that would naturally feed into an engineering physically based model. We look and we merge, we look at that data within the lens of engineering and science intuition, also within the lens of engineering and science principles, and we then create data that is optimal for engineering civil engineering driven decisions. And so we iterate that process based off of the results that we get from our machine learning model. The way we go about this for flooding, so I mentioned we start with the digital elevation model, which is an image. We start with land use, which is an image. So we take these images and we look at them on a watershed level basis. So the United States Geological Survey has divided the United States up into about 93,000 watersheds. And so for each of these watersheds, we can go and download the associated digital elevation model, land use data. And so watershed would look like what is shown on the image here on the screen with the red outline. We take that watershed area data, and then we partition it up into a grid, and then we store this information on the Databricks on the Delta Lake. And so we partition it by HUC, and then within HUC we have a partitioning by grid, which allows us to retrieve this information quite readily, both when we want to make predictions as well as when we want to train. And to give the scale at which we're working, so one watershed, we use Azure Batch to process these images into derivative images like contributing area, velocity of flow based off of Manning's equation, and so on. So we could have 7, 8 derivative images from a digital elevation model. We then go about storing that in data lake, Delta Lake with the partitioning scheme shown here. And for one watershed alone, you're talking about billions of data points. So you're talking about hundreds of watersheds that can be used to train a model. You're talking about trillions of data points. So the scale is quite immense, and the Delta Lake has helped us to manage that information, stored in part.
Hey, Mark, can you hear us?
Sorry, seems like we lost Mark. He had a couple technical difficulties. So if everyone does mind just bearing with us. we know how it goes when you're working from home. So hopefully he joins back in a minute. To the team, what I can do in the meantime, we had the poll running. So I would love to share the results with everybody so we can take a look at that. So the first question was, how do you commonly work with your data, not just geospatial? Check all that apply. It looked like the majority of you were using SQL outside of Databricks, using single node processing, and using native Spark. So those were the top 3 responses, which is great. What are the source formats of your geospatial data? Check all that apply. It looked like the majority of you selected shapefiles, database tables, text files as well. So, GeoJSON. So some, those are great. So it's great to see that such high percentage of all of those. What geospatial libraries do you view as useful to your use cases? Check all that apply. It looks like GeoPandas is 60%. So that's the majority there. And then what is your end user's preference for interacting with maps and visualizations? So high percentage of you all said Databricks notebooks and ESRI. Sorry if I didn't say that properly. And then last question was, how do you categorize your company's interest in Databricks delivering seamless scaled geospatial processing and analysis features? So it's 48% of you said would be useful, but not pressing. Great. So it was great to see those results in the poll. So thanks everybody for participating. It's really fun to see who's here. And then with that team, I know that we are still waiting to get Mark back. Were there any questions in the Q&A that we could answer live while folks were on the line and we're waiting for Mark?
I don't think there's really any major questions to answer live, just some things around Sedona. Was a couple questions were asked there. So we have been working with Sedona and other open source frameworks to have Databricks specific instructions. So we did point out in the Q&A the link to the Databricks install instructions on Sedona. And hopefully we can continue to expand on that to make it easier for people to understand. But generally, you're talking about Spark, usage of Sedona on Spark clusters, which obviously Databricks makes very easy. So there shouldn't be much friction, if any, to run what you would want using Sedona on Databricks.
Awesome.
Okay,
great.
So I think I'll move forward with my section, and yeah, if we have time, we can maybe get back to Mark.
Oh, looks like Mark just joined. Awesome.
Okay. Mark,
you're on mute, Mark.
For some reason, my internet cut out. I apologize. I can.
Mark, if you want to continue, you can. We haven't moved on it.
Okay, sorry. So where did I cut out? Around here on the slide?
Maybe back up one or two. Yeah, so you just finished talking about this slide.
Okay, yeah, so I'll pick up here. So this is an example of the data that we're storing. So we take the digital elevation model and then we derive derivative data. So contributing area, low is shown with green, high is shown with pink, which is the rivers. And then we can define different flow paths at different scales. So the large flow paths and the local flow paths. And then we can define the height above the flow path, the distance from the flow path for both these larger flow paths and these more localized flow paths. And we store all this data in the Delta Lake, partitioned by HUC, partitioned by the grid system that divides the HUC. And then we can recall it when we want to train, and then we can recall it when we want to make a prediction. We're talking for one watershed alone, billions of data points. In multiple watersheds, it's in the trillions. So we then, as I mentioned, there are 93,000 of these watersheds in the country. We take the digital elevation model, we create derivative images, we partition this image in a grid system, we break it down, we store it on the Delta Lake, and it's very efficient. It's Parquet file, so it saves on the storage space, and then we can efficiently recall it through the partitioning scheme that we have. We recall this data, We train the model on Databricks, and then we can deploy the model. In this case, we're using Azure machine learning to manage that. And we can deploy it and call it. And you can see here, we can get information quite rapidly for a given rainfall amount, what the flooding is. And you can see, I'll go into more detail on the next slide as to what that means. But the training, the machine learning model itself works quite well. So this is flash flooding. The area under curve is 0.89, the effluent score is 0.745. And this was also our first cut at it too. So we have ideas for improving it by adding more of the science behind hydraulics and hydrology into the process to refine this answer, as well as adding more data, potentially expanding the machine learning process, maybe adding a convolution layer to understand the interaction effects for flooding. And the other thing I will note is when we train this, we're pulling in the digital elevation model, we're deriving derivative data, and then we're training it based off of physically based models that the engineers have run within our company. So we run HEC-RAS to get flood extents for different storm severities. And so we pull that in, the machine learning learns how to link these features that we're creating that are dimensionless numbers to the storm, to the flooding severity predicted by the physically based model. And then we use the machine learning, we can extend that flood severity prediction to any watershed for any given storm severity. And we can get this quite rapidly. And what you're seeing here is the risk of flooding over different runoff amounts, which you could equate to different rainfall severities. Basically, rainfall, only part of it actually flows to the river. Some of it infiltrates into the ground. The part that flows to the river is called runoff. And so for different runoff values, we can see the flooding severity. And we've done some initial data comparison on this, and it's compared quite well to data on the ground. So for example, there's that catastrophic flood in Waverly, Tennessee. They had upwards of 16 inches in a very short amount of time. Let's see, about 12 of those inches were over 3 hours, and it washed through the city of downtown Waverly. It caused death, washed away cars. And we, after the fact, looked at that precipitation, the corresponding runoff value, and we ran that runoff. And we pulled the data for that area, digital elevation model, land use. We created the data for the machine learning model. We then applied the runoff value to that machine learning model. And this is the prediction that we got. Flooding is shown with blue, not flooded is just the aerial photograph. And it compares quite well to the aerial image of the flood right after the event. So we can see that there's flooding on the road here, which is shown here, the road, you can see some flooding here. And also this major flooded area here is shown with the blue here. And we also get the risk of flooding as well, because we're using logistic regression. So we could also expand this and add another layer of learning as well. And this is another example of flooding over the area. We can see this horseshoe of houses right here with the red roofs, and that corresponds to this area of the image right here. We can also see it provides, the horseshoe of houses is right here. We can see it corresponds quite well to even the risk of flooding. So we see this little finger of water extending in between the houses here, which corresponds to this higher risk of flooding, as shown by the darker purple color right here extending out. So overall, the machine learning model works quite well for predicting these flash floods. And we were able to manage all the data by using the Delta Lake, and that allowed us to bring all of this data in for training, billions and billions of data points for the watersheds for which we had physically based models produced by the engineers. So the other thing I'll mention is in terms of improving it, engineering and science expertise will improve the results. And so we're looking into how we can create features that are more, add additional features or create features that are more refined for predicting flooding. For example, adding in a feature that would represent the cross-sectional area of a channel or a flow path, instead of just subsuming that with the height above drainage multiplied by the distance from drainage. And the ML training scales across geographies because we define the features as dimensionless numbers, and we're able to work with this at scale using Databricks. And the other thing I'll mention is we're hiring 2 data scientists, one in North America and one in India. So if you have interest, please reach out to either me, Assad, or Aaron. Thank you for the opportunity to present here.
Yeah, thank you very much. Thanks very much, Mark. It was really, really interesting. Yeah, it was nice to see all that, really, how it really came together, and you're able to process all that data efficiently. I think Mark will stick around for a bit. So if you guys do have questions for him, please put it in the Q&A, and he'll try to get to them. Else we can try to get to them afterwards with either the geospatial experts on. Okay, so I'll start sharing my screen again. Okay, so now I want to go through geospatial on Databricks, and I'll give you just like a few slides to level set everybody, and then I'll walk through an example geospatial notebook to kind of show you how we address some of the challenges that we see of working with geospatial data. And then after that, I'll pass it over to Milos, who will go into a technical deep dive. So geospatial data is everywhere. Most likely, if you're working on a use case, there is some kind of geospatial aspect. Often, when you look at the key geospatial formats, right, or data types, you'll have vector and you'll have raster. Most of the time, people are working with vector. This is things like, points, lines, and polygons, right? So cities, points of interest. You could have streets and rivers, or neighborhood boundaries, right? Those are different examples of like vector style data. And that's probably the most common that we see, even though, when we look at raster data, that's when you're looking at, grid-based geometries and looking at these cells and surfaces, right? This could be things like looking at spectral data, like Mark mentioned with the elevation data that he was looking at. Yeah, and so these are the two primary. And so we're not going to cover a lot of the raster today, and primarily just looking at vector and different performance issues that you get. So when we talk about geospatial on Databricks, I'd say, well, actually one thing that's not mentioned here, is just, working with data in general is challenging. It's the name of the game, but geospatial data specifically, right? Like if you look at, the Open Geospatial Consortium, you take a look at all the different data formats that you have available. It's quite onerous to know how to ingest all of those different data types and make sure that you can integrate them into your use case. So often, when people some managers are like, the business is asking for the integration of their geospatial data in their project or use case, it's not as straightforward as people might think it might be, right? But that's not necessarily specific to Databricks. That's just geospatial data in general. But when we specifically talk about Databricks, right? So Spark does not have support for geospatial queries, and so we have to rely on different open source packages or different partner integrations to get that job done. And so, making sure that you kind of pick the right tool for the right job is really what it's about. Databricks doesn't have support for geospatial types. So there's no native geospatial type, and so you have to use these user-defined types. And most likely in the library that you're using, they'll have some kind of type constructor that will create these types, right? But you can generally define on how you want to, define your schema and serialize, deserialize type of data, right? But you have to be cautious sometimes, right? When you're writing these things to disk, or when you want to leave it in its native format. Those are all things that you have to consider, right? So it makes working with this more complex and not as straightforward. And then finally, Databricks, it doesn't have support for geospatial visualizations out of the box. And again, you're going to be using some of these open source libraries that will allow these geospatial plotting capabilities, right? But the data size still remains a challenge, right? And you often have to downsample, or you'll have to select a subset of your data in order to create visualizations and communicate your results back to the business. So these are the challenges, and we have our geospatial product manager, Kent, who will talk at the very end of this presentation. Okay, so when we talk about like a geospatial reference architecture, you're pulling in all of these different types of formats. And the beauty of the data lake first approach is that you can immediately just bring this data in without having to figure out how to parse all these different types of formats, right? And you can just create a historical, hasn't been tampered with data set, right, in the rawest form, right? Now from there, you can use different libraries to bring that data in, validate geometry, record projections, partition your data appropriately, right, to make sure that you can access it in a performant way, and then you would write out to, either well-known text or Delta, and then once you have this this refined data set, then you would want to create some kind of enrichments, right? You want to make your depending on what you want to do downstream, right? You might have different indexing applied. H3 is one that we'll walk through today. You might want to compute different aggregates and make sure that data is ready for analytics, right? And you can do the analytics either in third-party tools, Carto, Tableau, Esri, Kepler, or you can then continue to use some of these libraries like Sedona, GeoTrellis, GeoMesa to do your various like geospatial joins, different raster processing, or some of the ML work that you want to do. Yeah, and so this is just an example of when you pick up some common file format, you might have a library that has a point reference, right? And so you'll have like a lat long coordinate or a polygon geometry, right? And then these will be picked up as a user-defined type in the schema here, right? And so this is something you get by using a library like Sedona, for example. So when we refer to, okay, so we've talked about how to get that data in, different steps that you'll need. Now, when we talk about the actual data analytics flow, right, you'll do depending on what you want to do, right, in terms of your geospatial joins, do work with raster processing, you'll have to pick a library of your choice, right? Raster frames maybe for geospatial, GeoMesa, GeoSpark, these types of things for your specific use case, right? I saw in the chat, there was, or in the poll rather, like there was a lot of GeoPandas, right, that people want to use, and it's definitely convenient, and it might be the right solution for your team, right? But then to actually scale that out and use Spark to distribute that workflow, you're going to have to wrap it in a user-defined function, right, to distribute it to all the worker nodes. And so it's a performance trade-off that you have to take, right? Because you are going to take a bit of a performance hit by using these user-defined functions, right? But if you focus more on the open source libraries that are available to you, they're creating sets of user-defined functions and types that really focus in on the performance, right? So definitely just pick and choose what works for you and your team. But then from there, you can then take it to some like a modeling framework, right? You can use PyTorch, TensorFlow, Keras, track your results with MLflow, and then visualize your data, right? And I'll show how you can visualize that both within the notebook, or you can maybe even export it to a third-party tool to handle your visualization, or even some downstream data processing there. Just a quick time check. Yeah, so we'll, I'm going to give you an example. Indexing is a big part of it, right? There are different types of indexing. We're going to take a look at H3 which is the hierarchical indexing system developed by Uber, which breaks up the globe into a bunch of hexagons that vary in resolution size. And you know, some comparisons are like S2 and GeoHash, and I think Milos will talk about that. Yeah, and so the notebook that I'll walk through, just to level set people, you know, we're gonna use this H3 library, and we're gonna create a bunch of polygons, and we're gonna vary the resolution size depending on what we want to see. So I'm going to use the New York Taxi data set, and you know, again, these notebooks will be available to you. I'm going to walk through one, but all of the one will be, and the data will be available to you. So let me get out of here, and let me go over to the Databricks Workspace. So okay, so now we're in the Databricks Workspace, and the first thing that I'll mention is setting up the compute, right? So like we mentioned, Databricks provides great access to virtual machines and Spark, you know, that's managed for you. So we have one cluster set up here, and here you can pick like a specific Databricks runtime. You can specify the worker type, a lot of the memory and the cores, the count that you'll actually need. And the thing that I want to point out is that you can take a look at the libraries here, and you can see, or you can install the different packages that you might want to use in your workflow, right? So if I want to use GeoPandas, if I were going to take a look at the, if we want to look at the H3 library, we can have those installed, and we can just install new, and we can pick from either you know, all these places, or you know, have something custom that you've written that you can bring in, right? And so having this customizability is really strong and allows you to really pick the right tool for the right job. But cluster configuration is a big part of it, and making sure it's usually a pretty big barrier to entry. So usually using things like Docker files or some of the init scripts that you can configure here would be beneficial to setting up these libraries if they need a little bit more low-level configuration. So on the left-hand side here, I'm going to pull in the data using the repos functionality. So I'm going to come to my project here, and I have this one set up for a geospatial analytics, and I have a series of notebooks available. And so all these will be available to you. The resources library, this one will load all of the different New York Taxi data to set up these notebooks. So opening up this one here, the geospatial binning. At the top here, you can see that I am on my main branch, and I'm attached to that compute that we had set up. And so we're going to look at how to spatially index point data. So we're going to take our lat long coordinates, and we're going to transform them to the Uber's hexagonal hierarchical spatial index, H3. And thanks to Derek and Michael for setting these up. So I'm not going to run these for the interest of time, but first thing that you'll need to do is you'll need to import some of the libraries. Right, so we are going to use a Scala notebook here. You can pick the language of your choice, like the default language of your choice here. So it's just you know, up to the user. So you can Scala, Python, SQL, R. And so we're importing the H3 library. Then we're going to also use like a user-defined function to wrap this library up. So we want to take like I mentioned, the H3 library is going to convert the lat long to the H3 index, right? And so we're going to define a function here, convert to H3 address, that's going to take in our lat long, and then return. We're going to call this h3.get geo to H3 address, and we're going to create that H3 index. And now, in order to use it on the SQL and data frames, you need to register it as a user-defined function. So pulling in the data, so this data is already pre-configured. So let me see the data tab over here. So this is my database. I have, we talked about like the collaboration aspect, and having the meta store here where you have access to, maybe like a specific project, and then all of the different data sets that you might want to reference, creates that consistent view right across your organization and across the different people working on the project. Right, and so so then I can just pull in this type of data. So I'll pull this in. I'm going to read for the Spark table, green, trip data, bronze. Right, and we're using, in the previous slide we used the raw refined or raw enriched refined approach, but you can use, very often we refer to like the medallion architecture, like this bronze, silver, gold, where you're incrementally improving your data set over time. So we'll pull in our bronze data, and we can display that data frame right here inside the notebook itself. And you can see that we have, our pickup and drop off times, and then as well as our lat long that we can find. So this data set is going to go, we do a quick count on this, and we'll have 45 million records just looking at this. This is just for demo purposes. You can obviously get a lot higher, and Spark can really scale out with the size of your data, but for demo purposes, this is it. And this syntax here, I'm picking up the DB name, so this is picking it up from that Christopher Chalcraft Geospatial name, right? And so when you run your data set, you should be able to, it'll create a database for you to pick that up in a programmatic fashion. So H3 supports different resolutions, and what we want to show is how we can go and take a look at all those lat long coordinates that we had, and then build the different hexagons, right, at different resolutions, different scales. So this is, so we're just defining in a range. So we're going to go from 5 to 10, and then we'll define a function here that's going to essentially add the H3 index as extra columns to our data frame. Right? This is this is clear. This is a flex here. I think Michael or Derek, whoever wrote this, but this statement is definitely very concise. A little bit hard to read here, but yeah, you're picking up your column. You're creating your column prefix. So pick up H3 resolution, and then you're using that user-defined function that we defined above, and we're picking up the lat long, and we're going to get that H3 index. So when we run that on our data frame, we're going to come out with a data set like this. Now we can see that our schema is looking, we now have this pickup H3 resolution 5, 6, 7, 8, 9. And now when we take a look at our data frame here, so we had our lat long, and now we have all of these columns added to the end of our data frame. And now we can use this to figure out which resolution we need, and maybe if we can visualize it, right? So this is an example of how you would index your data, right? You take a library, you wrap it in a user-defined function, you apply it to your data set, and then you get this indexing available to you. Right? And that's really how we overcome that challenge, right? The user-defined function, now we have the indexing available. So we'll register a temporary table. So this allows us to run SQL statements on this fully indexed data set. And I'm just going to show you that when we increase our resolution, so we're going to take a look and count how many unique polygons are for each of these resolutions. And what we see is that, when we have a low resolution, we have fewer number of polygons. And then when we have a high resolution, we have a high number of polygons, right? And so that's referring to like this kind of plot here, right? So you have big space big space polygons beside it, or you can have this like really fine grained scale, right? And so it really depends on what your downstream process is going to look like and what compute you have available to you and your time frame and different business SLAs, right? So these are the kinds of things that you'll need to evaluate at this stage, what works for you. Yeah, and so I just want to go through here. So yeah, so we've coded this up in Scala. We've done the UDF, and now we want to take these index and we want to visualize it, right? We want to visualize it using a heat map, and ideally, right, it would be nice to visualize it where we're working, right, inside of the Databricks notebook, right, without having to you know, use different visualization software or tools to like export your data and really put a little bit of a blocker in your workflow, right? It's definitely more convenient to keep things integrated. So what we'll see here is that you can run these magic commands that will allow you to install things on the machine. And so we're going to do like a pip install, and we're going to look at Folium, H3, GeoJSON, right? And these are just things that we're going to use for plotting. So we'll pick those up. We'll import our libraries, right? You can see now we're using a Python cell within a Scala notebook. And so this is also convenient for the people who, you know, who might be more familiar with one language or want to use certain language features for a specific portion of their workflow. The Databricks notebook allows that kind of polyglot functionality, where you can flip between it, right? So, you know, there's a lot of really great Python visualization libraries, and so, you know, so we want to use that. So we'll take our, what we're going to do is we're going to take our Spark data frame, and, you know, now because we want to visualize it, we are going to have to convert it to a pandas data frame, right? By selecting a specific subset of our data, right? And so we're going to look at this resolution 8 from our fully indexed data set. I won't go through this, but you know, this is just some plotting coordination stuff, and we're going to use Folium to create that map. So these are just some of the plotting parameters. You can go and read through some of the library documentation on how to get this coordinated. But then now, when we have the map here, we can create this map using our pandas data frame that we selected, and now we have this interactive map display rendered here within the notebook. So you can see we have, you know, the New York City map displayed behind us, and then all of our H3 hexagons defined here with the intensity of the pickups being located by the color, right? And so, you know, this really just highlights, you know, two of the challenges that we looked at before, right? So how to take libraries like H3 and then wrap them in user-defined functions, and then get the power of Spark to handle your processing workflow. And then in terms of the visualization aspect, you can convert to pandas data frames, you could downsample your data set, and then create interactive visualizations in here, or prepare some data for some downstream processing in other tools like Cargo Esri or so on. The one thing that we didn't really touch on here is the user-defined types. But you know, if you use a library and you get, or if you take a look at some of the other notebooks here, this point and polygon one will go through specifically using, you know, Sedona to create that point data set, and you'll see the user-defined type there. And I think Milos might cover some of that. So that's all I have for the demo. Hopefully it was like a good overview of, you know, how we address some of those challenges with geospatial on Databricks and some of the capabilities that you have. You'll be able to find these notebooks along with Milos's demo afterwards in a repo, and we'll send that out by email. So we have maybe a few minutes here. I think, Milos, do you want to come on? We can you can continue on yours, and then we can maybe take some questions at the end. We can answer questions in the chat.
Thanks, Chris. That was a very good introduction, and it actually makes my first notebook a rather easier thing to present. So I will take the screen over. And okay, so we will transition now from what Chris has shown you into a bit more Pythonic approach. So we'll still consider H3, and we will consider Folium in our first notebook, but we'll try to approach it a little bit more from a paradigm shift perspective. That being that traditionally, when we were handling geospatial data on single node machines from Python, a very common pattern would be we have some GeoJSON data, we'll load it into pandas, we'll then start querying geometries in those data frames using libraries such as ShapeLimit. So how can we bring in those aspects into a distributed system now? So we have many machines, we have Spark on top of it, and we do have third-party frameworks, but can we approach it from Python native perspective? So can we just leverage good old Shapely, maybe a little bit of geospatial indexing such as H3, similar to what Chris has introduced. Maybe we do have preference towards S2 because we're handling geometries at a much finer detail level, and we do need smaller index sizes. So we'll try to touch on a few of these concepts. So I will, these notebooks will be shared. They do have a brief introduction to the topic and type of questions we're trying to answer in both in geometric and geographic operations. Such questions could be from the point and polygon type of operations, such as connect me these addresses to these building shapes in my area, and you can see a visualization of such problem. Or we can think of polygon to polygon type of operations, such as I have these land parcels and I have these like water bodies. What is my what are my intersection areas of flood risk? And it can tie back into some questions that we talked earlier in this call. Other type of questions that can go back to point and polygon would be tracking maritime vessels and having areas of interest such as vicinity of ports or areas that are known for criminal activities. So before going into code, one of the questions that comes to mind is why is point and polygon hard at scale? It has to do with how Spark optimizes the way it handles large volumes of data. It can optimize simple logical operations that define a join. So this number is equal to this number. I will be able to easily, under the hood, define portions of data that should go to same machines on a distributed system. But when we come with a Boolean expression that is complex in nature, such as point and polygon, yes, the answer is still a Boolean, so relationally speaking, it makes sense, but mathematically speaking, it's not always the same cost when I'm comparing a point to a polygon. The more vertices the polygon has, the more expensive my question is. And if we have large skews, it's going to start becoming a very problematic thing to scale. If we go back to the topic that Chris was showing about New York City taxis data, you can expect most of the trips, or at least large volume of them, to happen in Manhattan area. And that can cause your joins to be very slow because the way Spark will handle this under the hood will exhibit skew. So one answer to that would be it's easy to say traditional divide and conquer, but that's why we have these indices. So we represent our geometries as a set of indices, and we can perform both our point and polygon joins and our polygon to polygon joins via those representations. Now, if we observe H3 as a index system, there are some challenges, and we're going to visualize those briefly. So first, we'll set up the libraries that we require to handle this consideration. So that will be your GeoPandas to load the neighborhoods, your H3 and S2 to represent the neighborhoods in two different ways. Your shapely to handle some of the operations on the geometry level, and Folium to visualize them. I will fetch New York City data from the Gov page, and you can easily fetch them via this line, and we'll unpack them and put them into Databricks accessible file system. You can rerun these these cells at your convenience, and they will make the data available at your username. Just please make sure that you update the username to reflect your username on your platform. When we load the shapefile, we'll actually notice that this is expressed in a different coordinates reference system. So we'll just make sure that everything is in lat long. You can easily Google the code if you're not familiar with it, and it's 4326 that will make sure all of our vertices of polygons are represented as lat long pairs. Just to make sure that everything is looking good, and we can easily just check it in GeoPanda's plot. And yes, this is indeed New York City and all of the polygons. So we can also represent such polygons in Folium, just so that we have a coherent way of viewing between different notebooks, as Chris was also using Folium. All good from the geometries. We have some geometries now, how we can make them more parallel in nature. So what we will do is we will represent those polygons using the polyfill method that is here, that is readily available from the H3. And as soon as we run that and visualize the data, we will see a problem occurring. I'll zoom a little bit so that you can see it. There are two problems, and they happen usually when you're trying to rasterize your data with a lot of details in a finite set of points. So this is also like if you think in old days, low resolution screens. So what happens here is we have some pixels that are missing partially, and we have some pixels that are overstating the area. These two problems are not the same in nature. The missing areas are worse than the overstating, from the perspective that if I overrepresent my geometry, all the points that fall in will be there, and I can do a post-processing filter and drop the false positive, but I will never be aware of false negatives if I'm missing. So one way around it will be to buffer our geometries by a appropriate size. Because H3 is a global index, it will be susceptible to local curvatures. So because the Earth is an envelope and we're trying to fit something around a spherical system, there will be some curvatures that are not exactly the same near the poles and near the equator. So we can use the side of the individual index at a given resolution, but that may cause errors in some areas. So a better thing is to fit a minimum rotated square and take area of that square, take a square root from it, and then take a half of it. That will still assume that even with the curvature, the individual indices are very close to a square representation rather than to the rotated rectangle. But that will be a smaller error than in case you're just using the side. So if we follow these exact, sorry, I went ahead of myself. Another way of representing this would be using S2 as a alternative indexing system, and has the same APIs. We do have a binding that's available in Python that tries to mimic the APIs of H3, so you can have a coherent representation. It does return the results slightly differently, whilst H3 returns a set of index IDs only. S2 API returns a set of index IDs together with the boundary of the geometry representing the index itself. So you may need to do some accommodation for that API differences. And we will perform the same representation. In this case, we'll just use the polyfill of S2, and we make sure that, yeah, everything is running. So we visualize the first index. When we plot that representation, we'll see a slightly different case. So whilst H3 uses a centroid point to make sure that the index should be included in a representation set, S2 in this case uses intersection operation between the index geometry and the geometry you're trying to represent. So the blind spots won't be there. If there is even the tiniest intersection between the geometries, they will be included, like, for instance, this one that's entering very little into the original. So this looks better and easier from that point of view. However, there are other challenges that we'll see briefly down the line. So S2, while it brilliantly handles those blind spots around the edges, this binding does not handle well the geometries with holes. So I will create here a geometry that's exactly the original one we were using to represent, but I'll carve in a hole in it, and I'll try to represent it via S2 like I did before. And when we perform that operation, actually see this, and that's not what we want to see, because the set of indices should only ever represent some indices that share area with this ring that we see here. So the internal part is a hole that we do not want to be included in the representation. So we'll need to do some thinking from the S2 side. That's a little slightly different from the H3 side. So there is a problem on both index system, but the approach we are proposing, it's actually solving both at the same time. And it can be applied to an arbitrary index system. And we will have a blog that will be shared with the link to it will be shared with the other content that talks about how to apply this in a planar system, localized planar system using Nordings and Eastings. To be precise, we did this with a customer in UK territory, so we used British National Grid, but the same principles apply to any Nording Easting coordinate reference system. Okay, so going further, how can we ensure a lossless representation? We can buffer, as I or before mentioned when I went a little bit too hasty, we can buffer our geometry, we can buffer it by a specific amount. That specific amount will be take the centroid index that corresponds to geometry, fit a minimum rotated square around it, then determine the side of that square. It will probably be a rectangle due to curvature, but the error will be minimal in that approximation, and then take half of it. That will most closely represent a radius of the minimum fitting circle around an index that corresponds to the centroid point of the geometry you're trying to represent. Alternative is implement your own or use a library that implements a minimum fitting circle and extract the radius. We wanted to be rather lean with respect to how many dependencies we have in this solution. So we tried to do what can we do with Shapely only. And we will now use that method to represent our geometries. And we need to verify that this simple trick has at least solved our first problem with H3. And indeed has, to some degree. There is an additional problem that's lower in gravity than the previous one. We do have some that true negative indices included. But again, as we said, we can apply post-filtering on the indices that are close to the boundary of the representation to make sure that we do not include any false positives. So that leads us to the next point. We can represent, sorry, I will just go back to our visualization because it's a good starting point before we jump into the code. Out of all of these indices, what we can, just by observing it, identify is not all of these indices are same. in nature. So equality for all, but not in this case. So the ones that are fully contained and don't touch the border can be used as a fast operation. So any point that falls within any one of these indices that are fully contained within the original geometry, we know belongs to the geometry. Any index that touches the border, we can mark it as a border area index, and the points that fall inside of that one will require some post-processing. That the same logic applies if you have any holes inside of your geometries. The whole boundary will be treated as an extension to the overall boundary outside. So that leads us to a two-set representation. And what we will do is we will go through the polyfill indices. We'll check which ones do touch the border. We will mark them, and we will also do another trick. And I'll first walk you through the logical set of steps. So we'll mark all of the indices that fully are contained with the polygon and say, okay, these ones are core, they don't touch the border. You can use them as a short circuit for your join logic, both for the pointing polygon and any other polygon to polygon operation, because you can re-express your relations between geometries via these bits. The indices that do touch the border, you'll need to understand which portion of their representing geometry, so the hex or the rhomboid when we're talking about S2, is inside of the geometry or that you're representing, and which part is outside. So you do need to perform some intersection there, but a local one. And while you're doing it, you may as well store that portion of the index or that portion of the geometry. So if I zoom in here, that would be from this vertex till here, till here, till here, and till finally here. That area there, we're going to save it and we're going to call it a border chip. What that brings us is that when we're checking points that fall within that specific index, we do not need to perform pointing polygon against the original, more complicated geometry. We can compare it against that localized view. That, on average, is actually a simpler geometry. And if you remember earlier when we talked about the cost of performing an operation against the geometry is proportional to its number of vertices. So if you have a small localized representation as there, like a zoom in, well, first, that portion is independent of the rest of the geometry, so you can send them to different threads, becomes very parallel and adaptable to how Spark processes things. And in the same time, it's also cheaper because it's a simpler geometry. So you shuffle less data when you're doing the Spark shuffling. You perform the lookup cheaper because it's a cheaper mathematical operation, and they are decoupled now. So different indices can actually fly independently, and you can collect the result at the end after all of them are processed in parallel. So, and that's what we're going to do in this method here. So we have put quite a bit of commentary around so that it actually maps to the logical thinking and when the steps happen. And basically, the logic is as I explained. Get all of the indices, walk through the ones that are completely contained, mark them, walk to the ones that touch the core, touch the border, compute the localized chip and store that chip together with the index, and return a set of these. And we can visualize one of those. So it will look different than before because we will have now an index. We will have a flag that will tell us whether it's a border. So do we expect a chip to be stored with it, or it's a core where we don't really need to store the chip. The chip is the whole index geometry itself. And we have stored the chip as a binary format. This is because well-known binary, it's actually more compact than well-known text because of different precisions in double can cause the strings in well-known text to become very arbitrary. Whilst in well-known binary, for the same number of vertices, you can expect the same size of the data footprint. Okay, so
And Milos, there's a couple questions that came in.
Sure.
Michael, if you wanted to read them out, if that's okay.
Sorry, I have my mouth full.
No.
Sorry about that. Do you mind reading them? I'm sorry. It's just the first two there.
Sure. All right, Milos, these are for you. From Aaron, would H3 actually help for something like a point in poly for census block group query rather than indexing the geometry or a reference geometry is used?
Whenever you have skew in data and census data will be skewed towards polis types, so cities, towns versus rural areas, this will help you because you start partitioning those areas into subproblems, and you can actually say to Spark, I'm skewed on the H3 index. Further down that, I'm also skewed on the local authorities borders. And I'll show you how that looks like actually in the notebook number 3. So there will be an example of how we can do that second level skew hinting to Spark to even further help it handle it. I hope that addresses that one.
So it looks like yes from Aaron. Awesome.
Awesome.
And then from Amir says, in this case, you are only capturing the Boolean value for an intersection, but not the percent overlap, correct?
No, actually, implicitly, we do have the area. Explicitly, we do not. So that's a good catch. Depending on how you plan to serve your polygon to polygon relationship, you may want to add an additional field in this representation, which would be the area of the chip. Fully contained indices will have their whole area contained in that cell, so you can actually compute it very quickly. Whilst the chip, after you compute the chip boundary, you can actually construct a polygon shape or a multi-polygon, because intersection between a original geometry and an index can result in a multi-polygon for a very non-convex shape, and you can compute that area and store it there. That can be beneficial if your query of interest is how much do these polygons intersect. In that case, that would be very useful.
Milos, there's a couple of questions around just, the nature of how you get the parallelism out of this mosaic or chipping strategy. If you could take a step back and maybe just explain a little bit more about how that flow works, like what you do with the geometry, the fact that it gets, broken down for parallelism, how you're handling skew. You don't necessarily have to show code, but if you just talk through it, I think that would help.
So I was thinking to do that in the notebook number 3, because we have exactly an example that goes through the pointing polygon, and we can touch it there. And also we have an example on polygon to polygon in notebook number 4. I can't take it now. It's just, do you think it's better now, or we wait for an actual example?
Oh, okay. I think that's great. Yeah, so there was maybe a little bit of not following the thread. So I just want to make sure we didn't lose anybody.
Okay, I'll summarize it quickly so that we have people follow better. So step back. When you have two choices when you have this kind of representation is any point that falls in any of these indices will, you can imagine it as being dedicated in a separate bucket of data, and Spark calls those runtime partitions. Now, you have two choices. You can send your geometry, the original one, to each one of those partitions. So if we have here, I don't know, 200 indices or something around that line, you will send this the whole geometry 200 times. And then you will compare it against any point inside of that index, the original geometry against each point there. So you're not doing any aggregation at runtime because you've represented it in the original sense. Now, an alternative is you say, oh, I know something more about how these indices work. Any index that's fully contained, any point that falls into it automatically falls inside of this geometry. So I can actually say all of the points inside of this index are a part of it. And Spark can start optimizing on top of that. So we can actually represent this geometry as these are the fast track indices. I don't need to do anything special about them. And the ones that touch the border, I don't know which portion of my the points that fall inside of me are inside of the geometry and which ones are outside. So I do need to do a post filter. And for that post filter, I actually need to execute a point in polygon relationship, which is mathematically more expensive than equality. Is this idea of the index inside of my set, which is much faster. Hopefully that brings a little bit more of the understanding of why we're doing this two-set representation.
Yeah, I think that's helpful, Milos. And I think it'll, as you said, the other examples will help further. Thank you.
Awesome. So last bit now is we can visualize now how this two-set representation looks like. So we'll fetch all of our indices, and this is how that previous image would look like now in two-set representation. Anything it's in light pink, any point falls inside, it's immediately part of geometry. It's an equality relation. Spark can optimize very well against this. So your skew, hence all of that is there. There is no user-defined function touching any of these. And in this particular resolution, they are a majority. Any ones that are dark pink, they will require post-filtering, and that post-filtering, unfortunately, at the moment, will require a UDF. However, because you have differently expressed your problem, that's a smaller portion of the entire computation. And because we have represented these as localized geometries, this is a simpler geometry, so it's a cheaper localized operation. And anything that we compute inside of this one is independent, let's say, from this one. So they can go to different threads and different partitions inside of the Spark. So it increases the parallelism. Not all data has of the same geometry has to go to the same partition, and that can help you prevent the problems of most of your trips are in Manhattan. So you can actually pulverize that into small indices. We have done the same logic just to show you that pretty much the same code can run against the any other index. So we've done it for the S2. The only reason why we have two functions is because of remember, the API of S2 polyfill is slightly different than the API of H3 polyfill. So we had to account for that. But the structure of these two cells is 95% the same. And if we visualize that, we get pretty much the same representation, now just with squares. The benefit of having both is if you go very small, S2 does go down to millimeter edge size of the index. H3 keeps it on a meter level. So if you do have a lot of very small geometries on a very isolated geographical area, S2 will probably be your better choice. And lastly, this method allows us to handle the holes. It does, because we do that chip identification, and we can actually drop any overrepresentation we had in either of the two approaches. And if I go just for the complicity, if I go to H3, the same applies. So I will not spend too much time on the notebook number 2 for the interest of time. This notebook will be here to prepare all of your data for the notebooks 3 and 4. And we have put a commentary around it, what we do. To quickly summarize, we will take a taxi strip data set, and we will apply a Python UDF that will convert pickup points and drop-off points to H3. So if I quickly show you, you'll expect 2 columns now to have the indices. From the neighborhood perspective, we will create a data set that actually contains, one thing worth mentioning before I jump to the other. Storing this in Delta can be very beneficial because we can use Z order on the columns. So what Z order does in Delta, it basically puts data that's logically close to each other, physically close to each other, so that Spark can optimize how it fetches the data at runtime. Because we plan to serve geographical data logically via its position, it makes sense that we physically collocate things that are close in the index space. So what we will do is we will perform a Z order by the indices we have computed. We will do the similar approach for our neighborhoods. The two-set decomposition will be applied, so the same code that we used in the previous notebook will be available here, and we will store the data on the disk. We will store it in an exploded manner. So we will have a index and its chip if it's a border index per row, so that we don't need to explode that before serving it for the join. And we will generate some randomized data set for polygon to polygon joins, just so we have some volumes, because 300 odd polygons on the New York City just doesn't show the volume of what we can actually achieve with polygon intersects. So we have created a couple of million of randomly offset polygons, so that we can actually show you how intersection will go, and that will be the last portion of the notebook. So the randomized data.
And Milo, sorry to interrupt you again.
Yeah.
There's another question if you're open to answering it from Lindsay.
Sure.
Awesome. Can you speak to the pluses and minuses of indexing the hexes that overlap the border at a finer resolution rather than computing intersection plus point in polygon?
Yeah, I can give you a brief answer, and the blog we will share actually has a whole section of discussing what is known as a theta type of join. So theta type join is a complex Boolean expression type of joins. Basically, Spark is not able to understand how to well partition the data with respect to the operation that's hidden inside of a UDF. So it actually resorts, usually, depending on the volume, it can be sometimes some optimizations, but on larger volumes, and we're here actually using millions of trips and hundreds of polygons, it will actually resort to nested broadcast loop join, which in simple terms, it's very close to what a Cartesian product is. And if you have 100 million points and you have, I don't know, a few hundred polygons, you're already ending up in billions of operations that you need to do. This partitioning allows you, at least on those that do not touch the border, to be fast-tracked, so that you can limit the amount of required, compare each one to each one portion of the data. So only the parts that are on the border will require that expensive iteration. Everything that falls truly inside will be fast-tracked, and it can be very optimized at runtime. Now, jumping into an example, so the point in polygon example, what we will do is the data we prepared from the trips perspective in the notebook number 2, we'll fetch it here. We can just inspect that it has the columns that we need. Some of the pickup will not be here. It's because it's physically stored. This can be a good hint for us that we have quality things to consider as far as the data we're fetching from open sources can have. And if you go here, you actually see that the data was reported with an error. So you can easily filter those out. And because you Z order on it, Delta will just skip it very quickly, as if it was a physical partition of problematic data. We will fetch the neighborhoods, and we can actually inspect it. So we have some chips that are border, and they do have the localized geometry, some that are not border and they do not have, and with their indices. And this will also be a Z order, so you can easily understand what is close to each other. And we can now proceed and define how a point in polygon relation will look like in this new space. So we need to prepare what is our join column on both sides. So that will be on because we have two options, either it's a pickup or a drop off. For this query, we'll select the pickup point. So we'll label it as H3 and we'll call the pickup. On the neighborhood side, we only have one option, which is the index of the chip. And we'll also label it as H3, and we'll say, please perform us a join on H3 and perform us an inner join. And this is where the magic of the two-set operation happens. We will first make sure that the matches that we identify are not on the border, meaning the point falls inside of an index, and that index is completely contained within a geometry. If that is the case, all we need to know is there was a match, and if that match happened, it will be a part of the outcome. Only if that was not the case, we will perform an UDF operation, which it's very simple. It just loads the local chip, and it performs the contains relation. This operator here is a short-circuited operator. So if the first portion is true, it will never execute the second portion. So you get that optimization benefits. Secondly, because these joins are done on a equivalence relationship, Spark skips that whole conundrum of theta joins and complicated relationships and everything, and actually can start understanding what to put where and how to avoid skews. You'll notice also, because I know most of the physical trips happen in Manhattan, I also said, yes, I did decompose these geometries, but still most of the volume happens in some of them. So please address the skew only on that side. And Spark is able to handle these optimization hints now. It was not before. And we can compute some aggregates just because we can now do neighborhood level aggregates as opposed to index level aggregates, and we can serve those. So I will perform that, basically a group by on an ID. This ID is an ID of the polygon, not the ID of not to be mistaken for the ID of the index. So if I go quickly just to refresh, this is the ID that we're grouping on, the ID of the geometry. You can have additional columns next to geometries other than an identifier and the WKB. In this case, it's a demonstrative data set, so it doesn't have much of the direct decorative columns. And we will convert to pandas the outputs, because at that point we will want to visualize it, and for that we will use Kepler GL in this case, just to give you also an alternative. So volume is great, the maps look amazing, but there are other third-party visualization libraries, and we do play well with most of them. I will just convert the WKBs at the serving time to WKT, because that's what the map library expects of us. And there is a wrapper that makes the serving of the map slightly more friendly. We can provide you. We'll provide you this method with the notebooks. We also provide you an example of visualization configuration, which you can modify to change color schemes and how this displays. So after that, we can actually visualize all of our neighborhoods with their different spans. After the join is resolved, we can also now start visualizing this maybe in a slightly different way. So if I want to assign height to each one of these, just so I can better visualize the skew that I was mentioning, I can go here and I can enable it, and I can select the field, which is my span, and you can see the power law emerging here. Most of the join is happening around the Manhattan and then around the airports, and this is a little bit hard to visualize with the single scheme. So I will also base it on the span. In this case, the more yellow, the more span has happened. So it was important that we can decouple this, decompose it, and hint the power law, because otherwise we would risk of having runtime errors because the partitions were really imbalanced. That's from the pointing polygon perspective, and we can extrapolate the same principle also to polygon relationships. The same set of libraries we will use again. So H3, Shapely, Kepler-GL. We will load the 2 data sets that we prepared in the notebook number 2 with our 2 set of randomized offset geometries. So a data set 1 decomposed and data set 2 decomposed. Both are roughly around 2 million, 2.5 million geometries. You are welcome to try running it against that full volume. In the notebook, we will run few subsamples just to be sensible. And how the Boolean description of these 2 geometries overlap translates to our 2-set representation. So if we have a fully contained index map of one geometry mapping to a fully contained index of another geometry, they do intersect immediately because the index is fully contained by both. Actually, it gets simpler. If the index is fully contained by either of the 2 geometries that you're trying to relate, there is an intersection because we know that's partially contained by the other. That means that the boundary crosses that area and it's fully contained by the other, you can short circuit that. The only moment where you actually need to perform some shapely level operations is when you have border to border, because you can have near neighbors depending on the resolution. So in that case, you do need to perform a additional filter as a UDF. And one other thing that you can do is in that set of border to border, in order to facilitate that something is an intersection, it's enough that one of those localized operation is true, then the overall outcome is true. So you can iterate, and then as soon as you detect one that is a proper intersection on a border level, you can return the true, and that's what we actually have done here in the code. So we'll iterate through all of the ones that are short circuit, return true if any of them is true, and then if we have to compute the border, we will only do it a minimum number of times.
And Milo, sorry to interrupt. You had a question from Alexander.
Yeah.
He asked, how well does a reordering with Z order behave with 2D data? Going from 3D to 2D brings plenty of well-known distortions, or is it simply better something than nothing?
Space filling curves, at least the ones we implemented for the Z ordering, if I'm not mistaken, are Hilbert curves. They do work well up to 5-dimensional spaces. After that, they start to suffer a lot. In this case, we're providing 2 columns. Obviously, what the that assumes is you have some variance in both columns, and you are in charge of how you identify that variance. So select the less variable column first, then the second, so that the system performs better. You're right, if you have high dimensional spaces, you can have this situation where, as you say, better something than nothing. So it's a bit of both. And I believe we are getting close to the punchline on this particular use case. So now that we have the UDF logic, which expresses that comparing of the individual bits and pieces, the join itself basically can be summarized. I perform the join between the indices and chips via the index ID. Once you identify the matches, collect them in a collection, and then execute that intersection logic against the collection. And an optimization on top of this is possible via user-defined aggregate functions, and that can bring you some benefits because you can shuffle less data. You don't require to collect the collection. But for the illustration perspective, it would have been an overkill, and it does require some much more involved code. And from the join perspective, what we do is we will join our left data set to our right data set. We've wrapped it in a function we can call multiple times, so we can run it against these different data sets. And after we have determined the join, we can group by the matches. The matches are defined by ID of the left side and ID of the right side. we'll collect a set, and we will perform the intersection, and we can drop the matches after because they will require some of the extra data to be represented. This is not mandatory, so you can remove that drop statement if you want to visualize. Given that the chips are stored as WKBs, it's a bit pointless for visualizing in a tabular sense. And we can perform some joints. So the first one we'll perform with 10,000 against 10,000. We can see that because we've done some randomization, there is not many matches. We can repeat that. And that took about 20 seconds. This is with a strong caveat. This does take about 20 seconds, but there was a data pre-processing operation that does take several minutes to decompose. Point being here, if your data is evolving very frequently, we'll need to think about other optimizations on top of this. If data is evolving less frequently, all you need to do occasionally is update some geometries that have changed. Then this is very good because you pay once the tax of the representation, and you can serve it very efficiently after. And if you have many layers that follow fall on top of the same locality, you can then have intersection views on cell level. So for your benefit, there are several reruns of different sizes, just to illustrate also that a few things can happen. With increased volume, you can increase serving time. At some point, you might see that time is falling because delta IO caching can kick in. So if you store your tables of delta and you serve it in multiple queries, we can be very efficient and ensure that a lot of it is served via caches on our VMs as opposed to going always to the disk. And that's also where Z ordering can help a lot because we can be efficient in predicting these queries. And lastly, just to show how that would look like in an example. So a lot of same things that was happening in the Kepler to prepare the data. So I selected a few examples and basically just to verify that they are intersecting. So I selected one on the left side and its matches on the right side. Because I done a randomized rotation and translation, you'll see these being out of their physical place, but that was the point. So just use the same data to generate a representative sample. And from my side, that would be it. So I'm happy to take any additional questions, or actually hand it over to Kent, and we can leave a few minutes at the end for questions if any are pending. Thank you.
I was going to say, Milos, maybe you can just answer this question real quick. The last one in the chat, which is, do you have any performance comparison using some sample set to illustrate how well two-set index perform versus original geometry intersection operation? I don't know if you want to reference the blog or... Yes,
precisely. We do have benchmarks published with the blog. So I will drop a link to the blog as the answer to this question. So we can have it there. And we'll follow up with that as a part of the follow-up content.
Great, thanks, Milos. You did leave me a few minutes. That's great. Yeah, hey everyone, my name is Kent Martin. I'm the product manager leading the geospatial effort at Databricks. I just want to spend a few minutes talking about our roadmap and address some of those challenges that Chris had mentioned earlier in the webinar. So Chris mentioned, yes, Spark not having support for geospatial queries and the reliance on open source or commercial packages, that you have to use user-defined types because there's no native geospatial types. And then just, some of the, again, challenges around visualization at scale with geospatial data. So I want to talk a little bit about how we're trying to address some of these challenges as we build out a roadmap for geospatial. First thing I'll start with is we plan to support native spatial types, starting first with both geometry and geography. So our focus is first on vector data. As we all know, there are many things, many data formats, raster, point cloud, all the things, but we're going to focus on vector because we know this is, common spatial data used by our customers. to use that data, we want to make it really easy and simple to ingest and visualize. On the ingest side, of course, we want to support loading from common sources like CSV, Parquet, or other spatial file data sources. I think we have some clues in the answers to the poll that we asked earlier about the file sources and data sources that people are using. So we're very much in tune with those requests that come from customers and the common way and common data sources that people are using. And then working with the actual spatial data formats themselves, of course, supporting the standards that everyone or mostly everyone should know about, well-known text, well-known binary, GeoJSON, and so forth. So making it really easy and familiar to work with spatial data. And then how are we going to expose and allow you to query and work with the spatial data? So we want to build out a set of functions and operations, kind of similar to what you'd see in PostGIS through SQL, through Spatial SQL, and expose those in Databricks SQL. So make it easy for people to work with, query their spatial data. So this is just the start of what we want to do. And I want to say and highlight, a lot of this direction comes directly from customer feedback. So yes, you had the poll at the start of this webinar, but we've also surveyed customers and spoken directly with them on customer calls. If you want to provide additional feedback, please make sure to raise your hand or leave a note in the Q&A, or even join the community forums, community.databricks.com, or reach out to your account team. We really want to gather a lot of feedback around geospatial to help us determine the things that we need to build. On top of that, what I'm talking about really describes the foundation for geospatial support, right? Types, ability to ingest and visualize, so sort of an end-to-end workflow. Also, supporting the common and standard ways in which you work with spatial data through SQL. We want to build out the Databricks platform to really work well with partners, right? We want to have tight integrations with, the world's popular and common spatial and GIS tools. One example of how we work closely with a partner, we actually announced last week on the Databricks blog. So you might have noticed Cardo's announcement for their beta release of the spatial extension for Databricks. And we're really excited about that because we have, customers who use both these tools, and we want to make sure that they get the most out of them, and really trying to meet customers where they're at, right? So if you use a different set of tools, we want those all to play nicely with the geospatial roadmap that's coming from Databricks. So I know most people will ask about, timeline. The best I can kind of hint at is we want to make a lot of progress in 2022. I can't say specifically at which point milestones will be released, but I would say stay tuned to our blogs and other announcements coming in the new year, and very excited to work with all of the Databricks customers who are doing geospatial analytics. So with that, I'm going to wrap up this sort of brief roadmap section and open it up for questions. Now, I know there were a few questions in the Q&A that were directed towards Mark Bartlett from Stantec. Mark, are you still on the call?
Yes, Ken, I'm still here. I believe I answered all of them in the chat.
Oh, did you go back into the chat?
Yeah, I did. Yeah.
I was worried that someone would be left over. Okay, great.
If anyone has any more questions, feel free to reach out to me. mark.bartlett@stantec.com. I can put it in the Q&A, or where should I put it, Ken? If people would like to.
Yeah, you could just put it in the chat if you're willing to share your email to a broad audience, and
yeah, sure.
Know that this is recorded and shared. That's fine.
Yeah, that's fine. Is that, I put it in the chat, does that work, or I have to put in the?
Yeah, I think that works. It's in the chat. If folks had specific questions for
Okay.
Mark, they could follow up directly with him. He's open to that. Yeah, so I think most of the questions have been answered. There are a couple other questions that are coming in now, fast and furious. I'll maybe read them out, and maybe Michael and Milos, Chris, you guys can all unmute, and we can sort of take some of these questions together if you don't mind.
Yes.
Yeah, go ahead, Neil.
I can read them. I do see that Michael has marked himself as answering the first one. So I'll start from the other ones, maybe touch the first one and I can hand it over.
Oh,
So,
actually, Milos, I had that
yeah.
marked for you. Sorry, go ahead.
Perfect. So I did work with one of my customers in UK around ingesting GeoPackage and actually leveraging Spark and ability to read portions of the large file to different thread. So you can scale both vertically and horizontally. So with the number of files and also against imbalanced files. We are planning to release that early in the next financial year as a blog, or maybe as a small Python pip installable package that can help you use that with PySpark. So stay tuned on that bit. But yeah, definitely GeoPackage is an interesting format and should be supported in our open source ecosystem. Around the GeoPandas size limit, again, if you think of one way to handle that is you can store portion of data in separate data frames and send to Spark a list of files you want to load. Use Pandas UDF to load individual GeoPandas data frames, and then standardize schema and combine that into a single Spark data frame. So again, thinking parallelly as opposed to, I have to fit this in one machine. What if I have 20 machines? I can use 20 smaller files, combine them, and then Spark will handle that for me.
Yeah, I could answer the question around estimated time frame for releasing native geospatial operations, which I answered in the earlier section. I kind of dodged in that we don't have a specific timeline yet, and certainly want to have that released in 2022. Of course, for us, if we can get to that as soon as possible, great. But I wouldn't expect it in the first couple of quarters of the year. But just again, stay tuned for further announcements and timeline around here. I'm sure all of us, product side, on the sales and field side, will be eager to show and introduce customers to some of the new stuff that we're building out.
Another thing that just for Chris's question around Sedona and indices, just everything we showed now will integrate with other frameworks, because as you saw, we do keep the localized geometries together with the indices. So you could add additional operations on top. The only problem that I can see is if you have multiple geometry columns in Sedona, you might have some challenges around storing that on disk. So there's a little bit of thinking to be handled around that.
See, I know I can see we're right at time for the webinar. I think Adriana, if we were planning to close out, just wanted to say thank you to everyone for joining in. There were at least 400 people on the call at the start of it, and a ton of really interesting questions. So yeah, Adriana, was there anything else you wanted to include around wrap up for the materials or sending stuff out?
We'll get you everything in the follow-up email tomorrow. So the recording, the deck, the notebook. So keep an eye out for that. And just thanks everyone for joining us. It was great to have you, and thank you to our presenters as well. Yeah, thank you everyone. Happy holidays.